All right, so today's video is going to look at stoichiometry, which is a funny word, but we'll kind of describe what it is by doing it as opposed to trying to define it. So first off, balanced chemical reaction. Here we got carbon monoxide plus hydrogen gas to make methanol, okay? Um, and when we balance this reaction, we just put a 2 in front of the H2 and everything works out. Now, what this means, right? So here's some things that it can mean. We can make one CO molecule plus two H2 molecules make one molecule of methanol. Or we could say a dozen of CO plus 2 dozen H2 plus 1 dozen make 1 dozen methanol. Now we can use Avogadro's number. So if we have 1, it's just 1 mole, or 6.02 times 10 to the 23rd molecules of CO, plus 2 moles, or 1.20 times 10 to the 24th molecules of H2, make 1 mole, or 6.02 times 10 to the 23rd molecules of methanol. So 1 mole plus 2 moles make 1 mole. And this is how we count. We count in moles. So 1 mole of CO plus 2 moles of H2 make 1 mole of methanol. So first we're going to balance this reaction, and we're going to look. When we balance this reaction, we have 1, 5, 3, 4. Okay? Well, that means 1 mole of C3H8 plus 5 moles of O2 make 3 moles of CO2 and 4 moles of water. This tells us how many moles of each reactant we need and also how many moles of product we'll get. So if we have 1 mole of this plus 5 moles of this, we'll get 3 moles of CO2 and 4 moles of water. So we can use that information for ourselves. Now, suppose we have 4.30 moles of C3H8 and we want to know how much O2 we will make. First, we look at the balanced equation, then we solve. Do it now. We're going to calculate the moles of CO2 formed when 4.30 moles of C3H8 reacts. Do it now. All right, so we have 4.3 moles, 4.30 moles of C3H8. And we want to find how much O2 we need. So we're going to figure this out in moles, all right? And we have to look at what is called the mole ratio. I know for every 1 mole of C3H8, because there's a 1 here, I make or need 5 moles of O2 just by looking at the balanced equation, right? There's a 1 here and a 5 here. Since I have moles of C3H8 here, I put 1 mole C3H8, 5 moles of O2. Things cancel out, and then I just multiply those two numbers. So when I multiply, let me get to the end, 4.30 times 5, I get 21.5, 3 sig figs, I'm good there, moles of O2. All right, so all I do is look at the moles that I start with. So the object I start with goes to the bottom. So if I start with moles of C3H8, I go moles of C3H8 at the bottom. And then whatever I'm solving for, in this case oxygen, goes on top, so I put a 5. And then I just multiply and divide. Multiply, divide by 1, 21.5. Okay, here's another equation. It's already balanced for you. And we want to know how many moles of O2 are required to react with 5.6 moles of H2S. Do it now. And how many moles of SO2 will be produced when reacting with 7.3 moles of H2S? Do it now. All right, so here's the balanced equation. We want to know how many moles of O2 are required to react with 5.6 moles of H2S. So I start with 5.6 moles of H2S. And I'm going to go from H2S to O2. So I'm going to go from H2S to O2. Since I start with H2S, I put that number down here, 2 moles of H2S, and then where I'm going goes on top, 3 moles of O2. So now when I put this in my calculator, I'm going to take 5.6 times 3, so I'm going across the top, and I'm going to divide my answer after I hit equal by 2, and I get 8.4. So my answer is 8.4 moles of O2. All right. So this is it. Where I start goes in the bottom, where I finish goes on top. So look at the next example. How many moles of SO2 will be produced when reacting with 7.3 moles of H2S? So I have 7.3 moles of H2S to start. And I'm going to go from H2S to SO2. So I'm going to go from here to here. So where I start goes in the bottom, 2 moles of H2S, and where I finish goes on top, 2 moles of SO2. Now you don't have to be a math genius to know that the 2's cancel out, and this cancels out, so 7.3 times 1 is 7.3 moles of SO2. But again, I put my given where I start, or the given goes down here, and then where I'm going to goes here. So if I'm going from here to here, it looks like this. If I'm going from here to here, it looks like that. But they both can tell me an answer. I'm going to do them both at the same time, okay? Then we can also apply this to mass. So let's say we have the same balanced reaction here. What mass of O2 will be required to react completely with 44.1 grams of C3H8? First, we need to find the molar mass of C3H8 and the molar mass of O2. Molar mass, I won't do that on the board, but we have C, molar mass of 12.01. We have 3 of them. Multiply and get that. Hydrogen here times 8 here, add them together. So the molar mass of C3H8 is 44.09 grams per mole. The molar mass of O2, molar mass of O16, I got 2 of them, 32 grams per mole is the molar mass of O2. Sorry. So knowing that, right, I'm going to find this answer. What mass of O2 would be required to react completely with 44.1 grams of C3H8? Do it now. All right, so bounce equation from before. We want to know what mass of O2 would be required to react completely with 44.1 grams of C3H8. So 44.1 grams of C3H8. And the tricky point here is that if I want to go from grams of this to grams of O2, first thing I have to do is find molar masses like we did. And then the next step is I have to find moles. I have to get to moles. So here's the first step, is that I want to convert this to moles. So I'm going to go from grams to moles. So I want to divide by molar mass. So the molar mass of C3H8 is 44.09. So I go 44.09 grams of C3H8, 1 mole of C3H8. Okay. Now this is the part that we did before. So we want to go from moles of where we start to moles of where we finish. Okay. So to do that, I start with this. So there's a 1 in front. So I go 1 mole C3H8, and I'm going to finish with O2, 5 moles of O2. This is my mole ratio step. Okay, moles of where I'm going to moles of where I started. And then I want to get to grams of O2. So if I go from moles to grams, I say 1 mole of O2 to grams of O2, which we've already determined is, I think we said 32, make sure I'm right, yeah, 32.00 grams of O2. All right, so divide by molar mass, mole ratio, multiply by molar mass. And that's how we go from mass to mass. Divide by molar mass of what we start with, do my mole ratio, what I start with, where I'm going, then multiply by the molar mass of where I'm going, okay? So I'm going to calculate this all up so we can get an answer of 44.1 divided by 44.09, hit equal, times 5, hit equal, times 32, hit equal. I get 160 on the dot, 3 sig figs out. So I just go 160 dot. of O2. So what this tells me is if I have 44.1 grams of this, I need 160 grams of O2 to make this reaction happen. All right, so here's another example. We got this balanced equation. So we want to do two calculations. We want to calculate the mass of carbon dioxide gas that is required to react with 10 grams of NaOH. And we want to calculate the mass of Na2CO3 that is produced when 10 grams of NaOH reacts with an excess of CO2. Do them now. All right, so here's our balanced reaction. Sodium hydroxide plus carbon dioxide gives us sodium carbonate and water. Already balanced. Easy balance, right? We just put a 2 in front of the sodium hydroxide and we got it. So the question is, we want to know how much carbon dioxide gas is required to react with 10 grams of NaOH. So when you see that 10 grams of NaOH, that's where I start with, 10 grams NaOH. And I want to go from NaOH to carbon dioxide, okay? But before I can do a mole ratio, I got to get the moles. So I divide by the molar mass of NaOH. Molar mass of NaOH. Again, we use our periodic table, right? 1 Na, 1 O, and 1 H. So 23.99 plus O of 15.99 plus H of 1.01. My molar mass of NaOH is 40.99 grams of NaOH in 1 mole of NaOH. Once I get the moles, now I can convert from NaOH to this. Remember, moles of where I start go on the bottom. 2 moles of NaOH. Moles of where I'm going go on top. 1 mole of CO2. So now I'm there. Now I want to go from moles of CO2 to grams of CO2. So as I see that, I know that for every 1 mole of CO2, I have what mass of CO2? Well, 12.01 plus 32 gives me 44.01 grams of CO2. Divide by molar mass, mole ratio of where we start to where we're going, and then we multiply by the molar mass of where we're going. So 10 divided by 40.99, hit equal. Divided by 2, hit equal. Multiply by 44.01. And I want 3 sig figs. I get 5.37 grams of CO2. So if I have 10 grams of sodium hydroxide, I need 5.37 grams of CO2 to get this done. All right. Now the second problem says we want to know the mass of Na2CO3 that is produced when 10 grams of NaOH reacts with excess of CO2. So again, we're starting with 10 grams of NaOH. And we want to know how many grams of this we're going to get. Same steps. We divide by the molar mass of what we start with. So 1 mole of NaOH. Then we want to go moles of where we begin. So we start with 2 moles of NaOH. And we want to go moles of where we end, 1 mole of Na2CO3. Then we want to go to grams of Na2CO3. So molar mass of Na2CO3, 22.99 times 2 plus C, which is 12.01, plus the 16 times 3. Whoa. Try again. 22.99 times 2 is 45.98, so that's the mass of sodium. We add to that the mass of carbon is 12.01. Then we add to that 16 times 3 because there's 3 oxygen. So the molar mass is 105.99 grams of Na2CO3 in 1 mole. I'm sorry, did it backwards. You're going to multiply. I want to go 1 mole of Na2CO3, and I want to multiply by 105.99 grams of Na2. So divide by molar mass of what we start with. Then we do mole ratio, where we start with in the bottom, where we're going on top. Then we multiply by the molar mass of what we're solving for, or where we're going. So 10 divided by 40.99 divided by 2 times 105.99. I want 3 sig figs, 12.9 grams of Na2CO3. So if I have 10 grams of this and an unlimited supply of this, when I run the reaction, this will run out. Once I lose the 10 grams, the reaction stops. In that process of using up 10 grams of this, I get 12.9 grams of this. The next type of calculations are molar volume. And this can only be used if we have gases. And these gases have to be at standard temperature and pressure. So 1 mole of gas is equal to 22.4 liters of that gas, as long as we're at standard temperature and pressure. So here's an example of a problem. Again, this equation that we've seen before. If we start with 253 grams of C3H8, what volume of CO2 will be produced? We need to know the molar mass of C3H8, which we've already calculated is 44.09 grams per mole. Do it now. Okay, so come back to this reaction. These are all gases, and we'll assume they're at standard temperature and pressure. So 1534. And the first question says if we start with 253 grams, so we start with 253 grams of C3H8. We want to know what volume of carbon dioxide we'll get. So what big of a container do we need to collect our carbon dioxide? So to do this, first step is we got to get the moles. We're going to go from here to here, but we're in grams. So we got to go from grams to moles first, all right? So what is the molar mass of C3H8? We said it was 44.09 grams of C3H8 and 1 mole of C3H8. Okay. Then we do our mole ratio going from here to here. What we start with goes in the bottom, so 1 mole of C3H8 to 3 moles of CO2. And then we're trying to find volume, so we use our molar volume. 1 mole is 22.4 liters, so 1 mole of CO2 is 22.4 liters of CO2. And this will tell us our volume in liters, which is kind of a big thing to try to measure, but we're going to try it anyway. So we're going to take 253 divided by 44.09 times 3 equal times 22.4. We get a number, pretty big number, 3 sig figs, 385 liters of CO2. So we're getting a lot of carbon dioxide there at that reaction. So when we use this up, we get this much. Again, molar mass to moles, mole ratio, where we start to where we're going, and then multiply by, in this case, volume of where we're going as opposed to molar mass. And then I guess that's the last one we want to do. Stoichiometry requires steps, right? We can make kind of a chart, okay, with this. We'll talk about the chart. I won't do it here, but we'll talk about the chart in class, and I'll put it on the agenda so that you can have a chart to look at if the chart's the way you want to go. But essentially, when we do stoichiometry, whatever we start with, we divide by molar mass to get the moles. We mole ratio, where we start to where we're going. Where we start goes in the bottom, where we're going goes on top, and then we multiply by where we're going, either mass or volume.